Welcome to another lesson of a friendly introduction to abstract algebra. In the last videos we discussed the fundamental homomorphism theorem, and in the next one or two videos, maybe three, we are going to discuss some corollaries from it that are known as the isomorphism theorems. We start with the so-called first isomorphism theorem, which is our proposition 27. As I've mentioned before, this terminology is not unique. Some authors call what we call the fundamental homomorphism theorem their first isomorphism theorem, and then this would be the second isomorphism theorem, so just that you don't get confused. Okay, what's the situation? As always, we have a group G, we have a subgroup of this group and a normal subgroup N. Then first of all, this expression here, sometimes called the complex product, at least in German, I'm not sure if this is also the English terminology, Hn, which simply consists of all these products. Hn, H runs through the group H, the subgroup H, and N runs through the normal subgroup N. In general, this here is not a subgroup, but if N is a normal subgroup, then this here is again a subgroup of G. This is the first assertion here. The intersection H intersected with N is normal in H. That is not so surprising, because N is a normal subgroup of the whole group. So these two factors exist as groups, because N is normal in G and hence also normal in Hn, of course, and H intersected with N is normal in H. So on both sides here I have groups, and these groups actually are isomorphic. So the assertion of both isomorphism theorems that we are discussing can be related in a naive way to dealing with fractions. If you had a fraction Hn divided by n, you would cancel the n. This is almost true, but not completely. You do not get simply h, as in the case of fractions, where you could cancel the n, but you get h modulo h intersected with n. So some part of n also remains here and must be factored out. This is the naive way to look at this isomorphism theorem, and it can be beautifully depicted like so. That's the reason why it's sometimes also called the diamond isomorphism theorem, because of this part here that looks a little bit like a diamond. So we have the whole group and we have the trivial subgroup consisting only of the identity. Then here we have a subgroup H, and here we have a normal subgroup N. These double lines always mean normal subgroups. Actually, N would be a normal subgroup of G, but it's only interesting here that it's then also a normal subgroup of Hn. Now, if two lines meet upwards, this means this is the smallest group that contains both of these groups. In general, this would be as a set, I would have to take the union of H and N, but this of course need not be a group. So I have to take the subgroup generated by the union of these two. But if N is a normal subgroup, then Hn, this complex product here, is already the smallest group containing both of those groups. Okay, if two lines in this diagram meet downwards, we always mean the intersection of both groups, which always automatically is a subgroup, and thereby the largest subgroup that lies in both of them. So this is how to read such a diagram. And now this isomorphism asserts that this factor group, which can be viewed as only this part of this diagram, is isomorphic, sometimes depicted like that, to this part of the diagram, which is H modulo H intersected with N. This is a nice way to depict this first isomorphism theorem. Okay, before we take a look at the proof, or at least an outline of the proof, the formal proof, A little bit more about the intuition behind this isomorphism theorem. If I take any element of this factor group here, it is of this form. It is a left coset with respect to the normal subgroup n, and here a representative is from this group, which simply means it is of the form h times n, where h belongs to capital H and n belongs to capital N. Now you can just think of it like that this n here gets absorbed into capital N. That's what I mean by here. So this coset is the same as this, or more formally, we proved that a long time ago when we introduced cosets. If the inverse of this element times this element lies in n, then the cosets, then and only then are the cosets the same. And this is clearly true because H inverse Hn is of course n, which lies in capital N. So one way or the other, these here are the same. And now you might think, well, then this factor group here can be represented by the elements of capital H. So I would get this isomorphism as expected when dealing with fractions. We could cancel n, but it's not quite that simple, because if the intersection is trivial, then it is true. Then every Hn represents exactly one coset here, and we have an isomorphism between this factor group and H itself. But in general, when this intersection is not trivial, we cannot have a one-to-one correspondence between this factor group and H itself. Why? Because if I take any element of the intersection, which is assumed not to be trivial, so there are at least two elements here, then it's always true that Hn is the same as the coset n, because H lies in n. So it gets absorbed into capital N. So this destroys a one-to-one correspondence between the elements of this group here and H itself. So we still need to factor out H intersected with N to get a bijective correspondence. That is roughly the idea behind this first isomorphism theorem. Okay, but now let's take a look at the formal proof, or at least we sketch an outline of this proof. This would be an excellent exercise to try to fill in the details yourself. Okay, first of all, you need to show that Hn, this complex product here, is indeed a subgroup of G. And as this is not true in general, this relies, of course, on the fact that n is a normal subgroup. So you should try to prove why when n is normal, then this becomes a subgroup, simply using the subgroup criterion and the fact that n is normal. Now we're considering almost the canonical projection. I'm a bit sloppy here. We're not going from H to H mod n, but from H to Hn mod n. In the following sense, is this almost the same as the canonical projection? We map H to Hn, the left coset. And if we think of H as being written as He, then this is indeed an element not only of H, but of Hn. Yeah, we simply take the inclusion map without writing it down from H to Hn, because any H can be written like that, and because E is an element of n, H, which can be written as He, can be viewed as an element of Hn. Okay, and then it's not so surprising that this is an epimorphism, and the kernel is exactly H intersected with n. Of course, you have to verify or fill in all the details, but this shouldn't be too hard. And now the assertion here simply follows by using the fundamental homomorphism theorem, because then H modulo the kernel of this homomorphism, which is this intersection, is isomorphic to its image, but because pi is surjective, the image is this factor group Hn mod n. So if I read it from there to there, the fundamental homomorphism theorem simply gives me this result. Okay, we won't be using that too much or at all in the future, but here's a nice example illustrating the application of the first isomorphism theorem. We prove that S4, the symmetric group on 4 elements, divided by the Klein-4 group, V4, is actually isomorphic to S3, the symmetric group on 3 elements. Now, by simply using Lagrange, well, first of all, the Klein 4 group, which consists of these double transpositions and the identity, is a non-cyclic abelian group of order 4, the only one actually that is non-cyclic, is a normal subgroup in S4. I'm not sure if we proved that, but that is not too hard to show, and has 4 elements. So by using Lagrange's theorem, we see that this group here has 6 elements, because the order of S4 is 24, 4 factorial, divided by 4 is 6. So this is a group of order 6. And now, if you already know that there are only 2 isomorphism types of groups of order 6, namely S3, the non-abelian group, and Z6, Z modulo 6, 6Z, the integers mod 6, which is abelian, then it's easy to see, because this is non-abelian, that it must be S3. But we do not want to use this classification of groups of order 6, but we want to use the first isomorphism theorem instead. Okay, then the argument goes as follows. Okay, we take the following 2 elements of S4. The transposition tau, which interchange 1 and 3 and leaves 2 and 4 by themselves. So I could write it like that. That's, to indicate that it is an element of S4. And the 3 cycle 1, 2, 3, which leaves 4 invariant, both elements of S4. And then it's not hard to check that the subgroup generated by those 2 permutations is this here. For example, if you compose tau sigma, you end up with 1, 2, and so on. So you write down all the words, all the powers of these elements, and you end up with exactly these 6 elements, which are clearly isomorphic to S3. They are not S3 because those are viewed as elements of S4. But when I simply drop the 4 that I do not write here anyway, then clearly this is isomorphic to S3. So this subgroup generated by those 2 elements, which I call H, is an isomorphic copy of S3 lying in S4. Then clearly the intersection with the Klein 4 group is trivial, because the Klein 4 group contains these double transpositions, and obviously they have no elements in common besides the identity. So we can use the first isomorphism theorem, which asserts that the complex product HV4 divided by V4 is isomorphic to H divided by the intersection of those groups. This is exactly what we have here. But since this intersection is trivial, this factor group, of course, is isomorphic to H, because the cosets look like that. Sigma it, because this here is the trivial intersection. So by simply cancelling this here and mapping this to sigma, I have my isomorphism between this trivial factor group and H itself. Okay, now we apply Lagrange's theorem. The order of this group here is this quotient. And by this isomorphism, this equals the order of H, which clearly is 6 here. So therefore, the order of this complex product is the order of V4 times 6, so 24. But this means that this must already be the whole group. It is a subgroup of S4 with order 24, so it must already be S4 itself. So for this quotient, we get S4 mod V4 is HV4, we just proved that, mod V4. And by the first isomorphism theorem, again, what we did here, this is isomorphic to H, which we saw earlier is isomorphic to S3. So without almost any messy calculation with permutations, except for verifying this here, we arrive at this result that the factor group S4 mod V4 is isomorphic to S3. And that was a little application of the first isomorphism theorem, which otherwise I think we won't be needing that much anymore. That's it for today. Thanks for watching, and I'll see you soon. Bye bye.